Okay, great. So yeah, we're really excited to have Alexandra, and she's going to tell us about a really cool new way of doing somewhat homomorphic encryption.
Thanks so much. Thanks for having me. And so hi everyone, I'm Alexandra. I'm a grad student at MIT, and I'm going to talk today about building homomorphic encryption from new assumptions. And this is joint work with my advisor Henry and with Yael and Vinod, and it appeared at Eurocrypt a couple months ago. Okay, so an encryption scheme is homomorphic if it lets anyone perform computations directly on encrypted data. So to be a little bit more specific, we say an encryption scheme is homomorphic for a class of computations F if the following process works. So first, we're going to have our user sample a secret key and an evaluation key. And our user now is going to publish its evaluation key, and then it's going to publish encryptions under its secret key of any messages of its choosing. So here, for example, we're going to publish encryptions of x1 through xm. And now any party that has received this evaluation key and these ciphertexts can evaluate directly on this encrypted data. So here, our server can take any function f in the supported class, and it can build the ciphertext that encrypts the function f applied to x1 through xm, crucially, without ever decrypting and without learning anything about the underlying encrypted values. So to be a little bit more formal, we say an encryption scheme is homomorphic if it satisfies these three properties. So first, it needs to be correct, which really just means that the ciphertext produced by the server here really does decrypt to the function f applied to x1 through xm. And for the purposes of this talk, we're going to be happy if this is satisfied with good probability. So think of this as something like probability 2/3, and you could always amplify this with repetitions and sort of taking a majority vote. Okay, the second property that we need is for our encryption scheme to actually be semantically secure. So what this means is that the evaluation key, together with all of the ciphertexts, should computationally hide the underlying encrypted messages. And finally, we need our encryption scheme to be compact. And this compactness requirement here says that the bit length of all of our ciphertexts, so the ciphertext sent from the user to the server and from the server to the user, should not grow with the complexity of the function f that's being applied to them. And so really, one way to think of this compactness requirement here is that what this protocol is doing is it's outsourcing the evaluation of f to the server. So it had better be that the communication here is smaller than if the server just sent the description of f to the user. Right, a trivial protocol to build homomorphic encryption might have the server just concatenate all of these input ciphertexts and append a description of f, and we really want to rule this out. So this compactness requirement here really captures what we might mean by computing directly on encrypted data. Okay, and the second point I wanted to make is that you really only need to sample this secret key and this evaluation key once. And after this, you can use this key pair to publish as many ciphertexts as you want, and for the server to evaluate as many functions as it wants. So really, this is why the compactness requirement here is only caring about the ciphertext, because you can really reuse this evaluation key many, many times. And finally, the reason why we care about homomorphic encryption is because a long and very fruitful line of work has shown that if we can build homomorphic encryption schemes, then we get a whole bunch of privacy-preserving systems. So for example, you could imagine that this function f that's evaluated by the server here is a cloud computing functionality, or a machine learning model, or a genome analysis functionality. And so if we have homomorphic encryption, we can evaluate this without the user having to reveal its potentially sensitive inputs. Okay, so as the definition of homomorphic encryption implies, this is really a primitive that exists along a spectrum depending on the complexity of the functions that can be homomorphically evaluated. So at the bottom here, least powerful, we have classic private key encryption, which is not homomorphic, so you can't do any computations on ciphertexts. Then above this, we have linearly homomorphic encryption, which can evaluate only linear functions, so do only additions on encrypted data. And at the top, most powerful, we have fully homomorphic encryption, which can evaluate any polynomial time computation on encrypted data. So for this talk, you should just think of this as doing any number of addition and multiplication gates. And so really, in between here, there's a huge range, which we refer to as these somewhat homomorphic schemes. And the power of these schemes generally grows as they're able to evaluate more and more multiplications. OK, so what do we know? Well, one-way functions give us private key encryption. And a whole suite of number theoretic assumptions developed in the 1980s give us linearly homomorphic encryption. What's more, it turns out that you can use this number theoretic crypto to evaluate some nonlinear functions, so specifically to evaluate certain small depth branching programs on encrypted data. Then, in 2005, we learned that using cryptographic pairings, you can evaluate degree 2 polynomials on encrypted data. So this here really is one multiplication and then many additions. And then in 2009, in this huge breakthrough in cryptography, we learned that using lattices, you can get all the way to fully homomorphic encryption. And then again, recently, that you can get all the way there using the machinery of indistinguishability obfuscation. But really, in terms of building homomorphic encryption today, this is it. So we only have this handful of approaches. And if you want to homomorphically evaluate polynomials of degree 2 or higher, really everything we know either relies on lattices or on pairings, which are used here and then also under the hood in all of the I/O schemes that we have. So this talk is going to be about a new approach to building homomorphic encryption. And specifically, we're going to build a somewhat homomorphic scheme. So we're going to land in the middle here, in that we're going to be able to evaluate a few multiplications followed by many additions on encrypted data. And to build this scheme, really, we're going to combine two tools. So first, we're going to take a linearly homomorphic encryption scheme, which is this balloon here that's given to us by number theoretic crypto. And then we're going to see how to lift this linearly homomorphic encryption scheme into a somewhat homomorphic one by adding in just one extra assumption. And this is really an assumption that on its own is going to give us no homomorphism. So on its own, this assumption just gives us private key cryptography. But when we put these two things together, we get something that's much more powerful than either individual part. And yeah, so just to reiterate, this is the first homomorphic encryption scheme that we know of that can evaluate polynomials of degree 2 or higher that doesn't use lattices or pairings. And another sort of nice property is that it's also a pretty simple construction. So we're going to go through the whole thing in this talk. And so exactly what this talk is about is how we can combine this sparse learning parity with noise assumption, which we already heard a bit about just before lunch. And so we're going to combine this with a linearly homomorphic encryption scheme to build somewhat homomorphic encryption. And this somewhat homomorphic encryption is going to be of the flavor that at key generation time, we're going to pick some parameter n, that's polynomial in the security parameter. And now we can build ciphertexts, and any party that gets these ciphertexts can perform just slightly less than log n multiplications followed by n additions on them. Oh, and I should say that all of these operations here are over fq for some prime modulus q, which shows up both in our sparse LPN assumption, and we need linearly homomorphic encryption over this field. And q here can be any prime of at least 3. Yeah?
You say over fq and then we need the h, so you have issues with small plain text?
Yeah, so it's a good question. Basically, we can emulate computing over like mod 3 over a big DDH modulus if we know the output is small. Yeah. And all the intermediate values are small. Yeah. But you could also imagine making Q as big as the DDH modulus if you'd like. Yeah. Any other questions? OK, cool. So what I wanted to begin with is to mention two very important prior works that really inspired this construction. And so the first thing I wanted to mention is this construction by Dao, Ishai, Jain, and Lin in 2023 of homomorphic secret sharing. So what they showed is that you can use this sparse learning parity with noise assumption, even though it only gives us sort of private key encryption, to get some really interesting homomorphism. And so what they construct is homomorphic secret sharing, which is sort of the many-party analog of homomorphic encryption, where you need many evaluators that don't collude to evaluate this function f. And so really, one view of our results is that we're looking under the hood, and we're seeing that they're using a linear secret sharing scheme. And what we can do is we can replace this with linearly homomorphic encryption, in addition to some compression techniques that we'll see in this talk. And what this gives us is a way to turn this into a homomorphic encryption scheme. So really, we've gone from needing multiple non-colluding parties to just a single party that can evaluate this homomorphic computation. And a second view of our scheme is that it's really related to this Gentry, Sahai, and Waters' fully homomorphic encryption scheme from lattices from 2013. And so specifically, one view of what we're doing is we're replacing this LWE assumption with this code-based assumption, so with sparse LPN, and we're sort of tweaking their construction. And what we get out at the end is, instead of a fully homomorphic encryption scheme, a somewhat homomorphic scheme from this other assumption. So really, these two views give us the exact same scheme. And you can think of it either as boosting this to get homomorphic encryption, or I guess breaking this to get only somewhat homomorphism, but from a different assumption. OK, and so returning to our theorem statement, what we're going to do in this talk is we're going to start by jumping into this sparse LPN assumption. Then we're going to step through this construction of somewhat homomorphic encryption. And then I wanted to leave you with a bunch of open questions and research directions, because really, there's a lot that we don't know yet. OK, so let's begin with sparse LPN. So this sparse learning parity with noise assumption was introduced in cryptography in 2003 by Alec Novich. And it's based on the following problem. So say I sample a random matrix A, which is sparse. So A here is going to have dimensions m by n, and all of the entries are going to be values mod q. And when I say that A is sparse, what I mean is that every row of A is going to have exactly k non-zero entries for some sparsity parameter k. And so you should just think of k as super constant for this talk. OK, so I sample a random sparse A. Then I'm going to sample a truly random, so dense vector S of dimension n. And what I'm going to do is I'm going to publish A, and publish A times S corrupted with some random noise. And specifically, we're going to sample this noise here so that with very good probability, all of its entries are going to be 0, or each entry is going to be 0, but with some small, so inverse polynomial, so n to the minus delta for some delta between 0 and 1. So with this small probability, the entries are going to be truly random. So really, with this small probability, I'm going to completely corrupt the corresponding value of A times S. OK, so I'll sample A. I'm publishing A and A times S plus these errors. And I'm going to ask, can you distinguish this from a random sparse A and a truly random vector B? And it turns out, to the best of our knowledge, the answer here is no. So this is a computationally hard problem. And it's closely related to the hardness of random constraint satisfaction problems and other problems in average case complexity. And just to give you a taste of what this means for cryptography, so this problem here gets harder the more noise you add. So the higher this noise rate. And so what we know is that in higher noise settings than the one I'm giving you here, sparse LPN is actually implied by the standard LPN assumption. But that's not, no, we don't know this in this setting that I'm showing you here. And in this setting, which we'll stick with for the rest of this talk, what we do know is that this gives us constant overhead PRGs, some forms of multi-party computation, certain pseudorandom correlation generators, and also this very cool construction of homomorphic secret sharing that I mentioned. OK, and so one quick fact about sparse LPN, which was proved by Dao, Ishai, Jain, and Lin in this homomorphic secret sharing work, is that it gives you some form of key-dependent message security. So specifically, if you take any scalar x, and now instead of publishing A and A times S plus E, you add to this the scalar x multiplied by the secret key, it turns out this is still computationally indistinguishable from a truly random vector B. So really, the takeaway here is that you can sort of hide linear functions of the secret. And for those of you who want a more formal definition of what's going on here, really what's happening is that it turns out the hardness of sparse LPN implies the hardness of a related problem where the A matrices are non-zero along the diagonal, in addition to being sparse and random. And this here you can show is key-dependent message secure for these linear functions if your modulus is at least 3. OK, so really the takeaway here is just you can hide linear functions of the secret. OK, and so now we're ready to start building this somewhat homomorphic encryption scheme. And we're going to do this in 2 steps.
So just
yeah.
For q equals 2, it's actually false, or just the reduction breaks down?
The reduction breaks down. Yeah. So there's actually, in their paper, Dao, Jain, Ishai, and Lin show that you can make some variant of sparse LPN where you can still prove KDM security for q equals 2. So there, every sample is either k sparse or k plus 1 sparse. So yeah. But the current reduction that we have just for the sparse LPN problem doesn't work. Yeah?
And this is the only place where you need the modulus to be greater than
Exactly. This is the only place where this restriction on at least 3 comes in. Yeah. Yeah, good question. Any other questions? Okay, so let's start building this somewhat homomorphic encryption. And in a first step, what we're going to do is we're going to use this sparse LPN assumption to get a way to homomorphically add and homomorphically multiply. So this should sound kind of strange to you because I told you that just sparse LPN on its own can't give us, or we don't know whether this gives us homomorphic encryption. And in fact, there's a huge caveat here, which is that the scheme that we'll build actually has no compactness. So the ciphertexts are going to be really enormous, but they have one really nice property, which is that decrypting these enormous ciphertexts here is very simple. And by simple, I mean it just is going to require evaluating a linear function in the secret key. So then, in a second step, what we can do is we can add in a linearly homomorphic encryption scheme to sort of solve this problem and to shrink down the ciphertext and really get a compact homomorphic encryption scheme. And so now what I'll do is I'll step through each of these 2 ideas in much more detail. And really, I want to emphasize that step 1 here is where these 2 equivalent views of the homomorphic computation come in. So really, this step here is modifying Dao, Ishai, Jain, and Lin's homomorphic secret sharing scheme to work with just one party. And it's modifying this Gentry, Sahai, Waters fully homomorphic encryption scheme to, instead of using lattices, work with sparse LPN. And so we describe both of these in detail in the paper, and I'll focus on the second view just to give you one view in this talk. OK, so how are we going to do this? How are we going to homomorphically add and homomorphically multiply? Well, we're going to have a scheme that looks as follows. So what we're going to do is first, we're going to have our ciphertexts be matrices. So when our user wants to send encrypted values to the server, it's just going to send a bunch of matrices to the server. And now, when our server wants to evaluate some function on these matrices, what we're going to do is whenever our server wants to evaluate an addition gate, our server should just add these matrices. And whenever our server wants to evaluate a multiplication gate, our server should just multiply these matrices. So really, this should sort of, if you're familiar, ring a bell to the GSW scheme. And we're going to have one more property, which is that decrypting these ciphertexts should be linear. So when our server is done computing, adding and multiplying these matrices and sends it back to the user, our user just needs to apply a linear function to the ciphertext here to get out the underlying encrypted value, f of x. OK, so how are we going to do this? Well, sort of following in Gentry, Sahai, Waters' footsteps, we're going to have each of our ciphertexts satisfy a key equation. So specifically, the secret key in our scheme is just going to be a random vector s, which should really remind you of the vector s in our sparse LPN assumption. And now, to encrypt a value x, what we're going to do is we're going to build a ciphertext matrix into which we've embedded this value x as a noisy eigenvalue. So to be a little bit more specific, we're going to require our ciphertext to satisfy these 3 properties. So the first property, this blue equation here, says that if you take this ciphertext matrix C, and if you multiply it by this vector minus S1, which you can think of as like an extended secret key vector, what you should get back is the underlying encrypted value x multiplied by this extended secret key vector. So this here really is saying that x is sort of an eigenvalue, and this extended secret key is an eigenvector. But I'm going to allow some errors here. So I'm going to allow to add in vector e that is sparse. So specifically, condition 2 here says that each entry in e should only be non-zero with some very small probability. So another way to view this is that we need this eigenvector equation to hold in most rows, but some of them may be corrupted. OK, so that's the first requirement. And then the second requirement we have is that the ciphertext matrix itself should be sparse. OK, so these are the requirements we have. And so now I'm going to show you how to build an encryption scheme that uses this key property here to get homomorphism. So OK, so we just copied it over to the left. And so the first algorithm we're going to need is an encryption algorithm. And so this algorithm takes in the message x that we want to encrypt. It takes in the secret key. And what it's going to do is it's going to build a ciphertext matrix, first by just sampling this random sparse A matrix, and then appending one more column to it. And we're going to compute this column as the A matrix multiplied by the secret key S, plus some sparse LPN errors E, plus the underlying encrypted value X multiplied by this extended secret key vector. So the first thing to observe is that by this key-dependent message security, this here really does computationally hide the underlying encrypted value X. And so we get semantic security. And the second thing to observe is that this here really does meet this key equation. So in your head, if you think about taking the ciphertext matrix and you multiply it by the extended secret key vector, so minus S1, what you get is that these A times S terms cancel out. And so you're left with exactly the error vector plus the message times this extended secret key. So this is exactly what this blue equation needs. And also, we know that these errors are sparse. And because A is sparse, the whole ciphertext itself is sparse. OK, so that's encryption. So we can encrypt in a way that satisfies these conditions. And now we can also use these conditions to perform operations. So specifically, if we add two ciphertexts in this scheme, what we get is a ciphertext that encrypts the sum of the underlying messages. And really, the intuition for this is just that if you have two matrices that have the same eigenvector, and you add them, it still has the same eigenvector, and the eigenvalue is the sum of the corresponding eigenvalues. So to be a little bit more formal about this, if we look at this output ciphertext cx plus cy here, we can again think about multiplying this by the extended secret key vector. We can do some math, and then what we get is that the encrypted value is x plus y, so this is the sum of the messages, and the new error is just the sum of the prior two error terms. So indeed, we get that the new error is only going to be a factor of 2 less sparse. So each entry is non-zero with a 2 times higher probability. And also, if our initial ciphertexts were sparse and we add them, then the output ciphertext matrix is still pretty sparse. So we also can keep this condition. OK, so this was the first type of gate that we need. And now the only other thing we need is a way to multiply, which we're going to do really analogously. So if you have two ciphertext matrices, and you multiply them, what you're going to get is a ciphertext that encrypts the product of the underlying messages. And again, the intuition here is that this is because if you have two matrices with the same eigenvector and you multiply them, it keeps the eigenvector, and the eigenvalue now has been multiplied. So again, more formally, we can show this by looking at this output ciphertext and thinking about multiplying this by this extended secret key vector. And when we do this, and when we sort of group like terms, what we get is that the new message is the product of the underlying encrypted values. So it's now x times y. And the new error term is going to be this thing over here, which is y times the x error plus the x ciphertext times the y error. And really, the only important part here is that we know that the two errors are sparse, and we know that the ciphertexts themselves are sparse. And so we can sort of argue sparse times sparse remains sparse-ish. And to be a little bit more formal, if our ciphertext here has sparsity k, then what we get is that the error rate has only grown by at most a factor of k plus 1. Yeah?
What's going on in the rightmost column of the matrix C?
Yeah, the rightmost column is always non-zero, but sort of for this accounting of the sparsity growth, all we need to care about is the number of non-zero values in every row. So yes, it doesn't matter too much. This is really where the plus 1 in this k plus 1 here is coming from. Yeah, good question. OK, so we argued that we can still bound the error growth after multiplications, and also we can still bound the sparsity growth. So if x and y are sparse and we multiply them, the output again remains sparse-ish. OK, so really, the last algorithm that we need now is going to be decryption. And this, again, is going to be pretty easy given this blue equation here. So given a ciphertext matrix C, what the blue equation here tells us is that we just need to multiply by this extended secret key vector. And then when we do this, what we get back is the right-hand side here. So it's x times, again, this extended secret key vector plus some errors. And so all we can do here is look at the last entry of this. And with good probability, the errors won't be in the last entry, and so we can just return that as the decrypted value. OK, so again, this is correct by this blue equation. And also, I want to emphasize that decryption here is super simple. So what we're saying here is just computing a linear function. It's just saying, look at the last row of C and take the inner product with this and output it. OK, so really, these are all the algorithms we need. And we can zoom back out again. And so what we've built is a scheme where really the ciphertexts are matrices. The server is just adding and multiplying these matrices. As this is happening, they're getting less sparse, and they're getting more and more errors. But then at some point, our server can stop computing and send the ciphertext back to the user. And so what we see is that the scheme that we just built is correct. It's secure, and it's also homomorphic. And so to be specific, if our secret dimension is little n here, and if our initial error rate is something like n to the minus delta, then this scheme here is going to let us perform just slightly less than log n multiplications, followed by just slightly less than n to the delta additions. And this is great, because n really is just a parameter of the scheme. So you can make n as big as you would like to just match however many operations you want to use this to perform. So that's good. But unfortunately, what I just said should also be a huge red flag, because n is also the dimension of our ciphertexts. Right? These are matrices of dimension n plus 1 by n plus 1. And so what I just said is that to be able to compute more, you need to grow n. And so your ciphertexts need to get bigger and bigger. And actually, we end up with a scheme that's not at all compact. So specifically, because we can only perform a limited number of operations, any function f that the server could evaluate here, you can always write down in less than n to the delta bits. So really, what this means is that our function f requires at most n to the delta bits to describe. But what the server here is getting is ciphertext of size n squared, maybe less if you take advantage of sparsity. And what our server is sending back here, again, is of size n or larger. So really, it seems like what we did here is not useful at all. Right? Our server has to operate on and send around these huge matrices when it would be much better off just sending the description of f to the user. And sort of another view of like this barrier that we're running into here is that we actually don't know if sparse LPN can give any form of compression. So it's not known whether sparse LPN implies a hard problem in the complexity class SZK. And so really what's going on here is every time we add, the bit length of our ciphertext is doubling. And every time we multiply, the bit length of our ciphertext is getting squared. So OK, so this seems really bad. But the good news is we're going to try and fix it by adding in a linearly homomorphic encryption scheme. So specifically, what we have right now is a way for our server to get some large sparse LPN ciphertext that's encrypting some value x. And now our server can compute any function in this supported class f on this ciphertext to get an encryption of f of x, which again is huge. And so really what we would like is to now give our server a way to shrink down this huge ciphertext. So really, the dream would be to give our server a way to take this ciphertext from our huge encryption scheme and translate it to a ciphertext from a compact encryption scheme that encrypts the exact same value f of x. And the way we're going to do this is by observing just that decrypting this huge sparse LPN ciphertext is very cheap. So decrypting this guy is just a linear function in the secret key. And so because it's just a linear function, we can homomorphically evaluate this with a linearly homomorphic encryption scheme. So specifically, what we're going to end up doing is we're going to publish the encryption of our sparse LPN secret key here under a linearly homomorphic scheme. And so now any party that's built this large ciphertext encrypting f of x can just homomorphically run the decryption function to get an encryption of the output of this decryption function under linearly homomorphic encryption. And because the output of decryption is just the value f of x, this is exactly going to be a linearly homomorphic ciphertext that encrypts f of x. OK, so that's good. We fixed sort of half of our problems. So now we have a small output ciphertext. But you might still point out that our input ciphertexts here are huge.
When you decrypt, you just take like the top row or like just one row of the matrix?
The bottom row, exactly. Exactly. Yeah, you could imagine doing something more clever where you do some sort of majority and try to error correct, but for our purposes, we're just looking at the bottom row.
So you get some correctness error, right?
Exactly, exactly. And so here we're saying as long as the correctness error is less than 1/3, we're OK because we could just do repetitions and take a majority at the end. Yeah, great question. OK, so we're happy because we have small output ciphertexts, but still we have these huge input ciphertexts. But the good news is we can solve this by playing basically the same exact trick again. So specifically, instead of having our user upload the encryption of X using this huge GSW-style scheme, we're instead going to upload the encryption of X under some much smaller, so compact encryption scheme that has cheap decryption. And specifically, when I say cheap decryption, I mean decryption that falls in this class of functions f that we can evaluate. And if you remember, f here is this class of polynomials that have degree slightly less than log n, and then also slightly less than n to the delta monomials. OK, so why is this useful? Well, again, we can just do the same homomorphic decryption trick. So we can publish an encryption of our large, under our large GSW-style scheme of the orange secret key here. And now anyone who has this encryption of the secret key and this orange ciphertext can homomorphically decrypt it to get a GSW-style encryption of the same underlying value. So again, this is letting us translate from one scheme to the next using the homomorphism of the second scheme. OK, so what we can do now is we can just put these three things together. So in our final construction, we have these three encryption schemes. The first one is compact and has cheap decryption, so in this class of functions that we can homomorphically evaluate. The second scheme is this big GSW-style scheme from Sparse LPN, which is homomorphic but not compact. And the last scheme is compact and linearly homomorphic. So now what our user is going to do is it's going to start by sampling a secret key for each of these schemes. And then our user is going to publish an evaluation key, which is just going to contain sort of the key switching material to perform these translations. So really, you can think of this as a chain of encryptions of one scheme's secret key under the next. So an encryption of scheme 1's key under scheme 2, and then an encryption of scheme 2's key under scheme 3. And so now, when our user wants to send ciphertext to the server, it can just use this compact scheme 1, so these orange ciphertexts. And then our server can locally, in its head, translate these to these huge Sparse LPN-style ciphertexts, compute on them, and then finally shrink the output again to an encryption scheme that's linearly homomorphic. Whoops. And so really, what we get here is that all of the ciphertexts that are ever sent on the wire are compact. And really, all of the blow-up that comes from working with these GSW-style matrices using Sparse LPN is really limited to the evaluation key, and then all of the computation that just happens in the server's head. OK, and yeah, so just to emphasize, you only need to publish this evaluation key once. And after this, you can reuse this to perform as many evaluations and publish as many ciphertexts as you want. OK, so really, this is it. This is the entire construction. And I just wanted to mention a couple extensions. So the first extension is that as I defined homomorphic encryption, I defined it as a secret key scheme. But you could imagine a public key analog of this, where the encryptor and the decryptor aren't the same person. And to achieve this, really all you have to do is make scheme 1 here public key. And so, for example, we know public key encryption from constant sparse LPN from this ABW paper that was mentioned in the last talk. And so what this gives you is public key somewhat homomorphic encryption. But decrypting these ABW ciphertexts is more expensive. And so this eats into your homomorphism budget. And so really, when you do this, you can then only evaluate a constant number of multiplications and then poly-lambda additions. The second thing I wanted to mention is that, oh yeah?
Can you keep going? Like, what's stopping you from, like, after having the third key, and then publish another way to, like, keep going?
Yeah. So it's a good question. We're going to come to sort of bootstrapping in the open questions. The limitation is that this guy no longer has cheap decryption. So we don't have anything that has, at the same time, compactness, linear homomorphism, and then decryption in F.
And second question, so you need this public key thing here, because normally linearly homomorphic encryption automatically gives you public key, but here it doesn't because of this like multi-hop issue.
Yeah, and also, so it does, but you want to retain both being public key and being able to perform homomorphic operations. And here we really have this bound on the number of homomorphic operations. Yeah, that's a good question. OK. So the second point I wanted to make is that in this regime, where you're only doing a constant number of multiplications, you can work with sparse LPN with higher noise rates, which has been shown by these prior works to actually be implied by LPN. So if you only want to do many fewer multiplications, you can get homomorphic encryption from standard LPN and then linearly homomorphic encryption. And finally, the last extension is that I wanted to mention is that really all the ciphertexts that you're sending here are from these two schemes here. And these can be made really small. So for example, if these schemes here have rate 1, or what we call in the paper batch rate 1, which is just rate 1 when you amortize over many function evaluations, then your somewhat homomorphic encryption just sort of directly inherits these properties.
So can you just go back one? Or what is that? So with, I see. So here it's constant, and with the less standard LPN, you can do log.
Exactly. Exactly. That's exactly it.
And
Yeah.
for the log, do you get? Is it based on like? Do you only get quasi-poly security because of the like sparseness is so low, or you can even get some?
So we get the parameter regime we work in is hard against any polynomial time adversary. Yeah. Good
No,
question.
but you
Even
can't break
sub-exponential
it with
potential.
sub-exponential.
Yeah.
You can't break it with quasi-poly.
No. Yeah.
So it's
Yeah.
sub-exponential.
Yeah. Exactly. Yeah.
And also this majority trick, the way you kind of compose schemes, you can only afford to do it at the end. Because if you do it in the middle, you kind of say
Yeah.
parameters are good enough that you just do it at the end.
Yeah, the parameters for us so far are good enough that you could do it at the end. It's a very interesting question whether, so for example, you could imagine doing it here once you go to this linearly homomorphic encryption scheme. If you encrypt not only the secret key, but all degree 2 functions of the secret key, right? So all degree 2 monomials, and then you can imagine doing a majority of 3 things. We haven't found a way to make this, get more homomorphism out of it, but it would be very cool if you could in some way. OK, great. So this is really it. So this is the entire construction. And so now what I wanted to do is just mention what all the open research directions are. How are we on time? OK, we're still good. OK, so the first direction I wanted to mention is to improve this scheme's efficiency. And really, this scheme has one large limitation, which is that this evaluation key is huge. Right? This evaluation key here still contains this matrix that's just GSW-style ciphertext under sparse LPN. And so because of this, the bit length of this evaluation key right now is a polynomial in the description length of the functions that you can compute. So I think it would be super interesting to make this smaller. And maybe one concrete target here is to get sort of non-amortized efficiency. So right now, the reason we don't care about the size of this evaluation key is because you can reuse it to evaluate many, many polynomials. But in some settings, you have a user who just wants to evaluate one polynomial. And there, again, it had better be that the total communication is smaller than the bit length of f. So the target here would be to try to make the evaluation key, together with the online ciphertext here, really smaller than the bit length of f.
This is even just for addition, right?
Yeah. Well, we have a linearly homomorphic scheme, so that's sort of, you could use only that scheme. But yeah, it's a good question. OK, and the second thing I wanted to mention is that sort of if you were able to get around this limitation on the size of the evaluation key, then I think there's actually some reason to be hopeful here about the concrete efficiency of these schemes. And really, this is because you can take advantage of the sparsity in this computation. So this was also observed in the context of this homomorphic secret sharing scheme. But really, what we see is that if you want to homomorphically evaluate a low-degree polynomial, or any degree d polynomial, and you have, say, m monomials, and your initial sparsity is k, then the work for encryption is just k plus 1 field operation. The work for evaluation is just m times k plus 1 to the 2d sort of linearly homomorphic operations. And really, this here is sort of black box in the linearly homomorphic encryption. And decrypting, again, is just decrypting one LHE ciphertext. And so I think the reason to be optimistic here is that this sparsity k can actually be really small. So I said you should think of this as just super constant, and there are actually some other flavors of this LPN assumption which were explored by Applebaum and Cachlon, where you can make k like 3. So if k is 3, then encrypting is 4 field operations, And evaluating like a low-degree polynomial is just number of monomials times sort of 8 to the degree. So this seems like a nice property. That said, I wanted to give as an open question the fact that LPN and sparse LPN specifically sort of still need some cryptanalysis, and so we also need to sort of pick concrete parameters for this assumption. So by this I really mean we need to sort of determine what the size of this dimension n needs to be, which fortunately doesn't factor into the size of these 3 algorithms, but it does factor into the size of this evaluation key. Okay, so that's the first open question. And the second open question I wanted to mention would be to try to go lower. So can we get homomorphic encryption from even less? And so here, specifically, the open questions are homomorphic encryption from only sparse LPN, maybe only linearly homomorphic encryption, or sort of similar to this work, from some combination of sort of weakish assumptions. And so I don't know how to do this, but what I wanted to mention here is just sort of a different or more abstract or high-level perspective on our scheme and really how we're using each of these 2 assumptions. So the sparse LPN assumption and this linearly homomorphic encryption. And so really what I wanted to mention here is that Michancho in 2019 showed that you can sort of boil this GSW-style homomorphism down to really 3 properties, which are also really come up in all of these constructions of homomorphic secret sharing. And so these properties are, first of all, key-dependent message security. So this is being able to encrypt functions of the secret key. Second of all, having some sort of linear homomorphism or even weak linear homomorphism. And finally, being able to evaluate your own decryption function. And so what Michancho showed is that all of these 3 properties are satisfied by LWE. But interestingly, they're not all satisfied by sparse LPN. So with sparse LPN, we saw in the beginning, we do have key-dependent message security. But you can evaluate linear functions, except not compactly. And you can evaluate your own decryption circuit, except not compactly. And so really, this is sort of rescued by the addition of linearly homomorphic encryption, which buys us compression.
So 1 and 3 are really different from each other?
It's a good question. So I think you could get around 1 by doing some sort of leveled trick. So sort of switching the secret key each time you compute. But the way 1 and 3 interact is that really the abstraction Michancho introduced is this sort of linear decrypt and multiply paradigm. So where to do a multiplication, you first multiply where your ciphertext maybe is multiplied by the secret key, and then you're able to use this to then decrypt after multiplying. Yeah, that's a good question. So one thing here I just wanted to mention is that sort of one view of what's going on here is that we're decomposing the properties that you traditionally need to get homomorphic encryption across multiple assumptions. So instead of having one assumption like LWE with all of them baked in, we can sort of rely on assumptions that are complementary and then bias these things together. Great. And the last and maybe most thrilling question I wanted to mention is whether you can get more homomorphism. So really, the target here would be to get fully homomorphic encryption, say, from sparse LPN and linearly homomorphic encryption. And so we don't know how to do this, but what I wanted to do is sketch some approaches and where they run into trouble. So the first approach would just be to say, OK, let's find a way to compute more. So in this computation step in the middle here, we want to be able to evaluate more functions. And to do this, really what you need is a way to control the error growth. And so here I just wanted to draw an analogy to the world of lattices and LWE, because with lattices, when I say control the error growth, really what you need to do is you need to control the magnitude of these errors. And so the way schemes like GSW do this is they use bit decomposition, and this lets you keep the magnitude of the values in the ciphertext small, and so then when you do multiplications, you can keep the magnitude of the errors small. And so really here in this LPN world, the analogous thing that we need to do is we need to keep the number of errors small. So the number of locations that have been completely corrupted by our sparse LPN noise. And really what's going on here is that the way we're doing this is by keeping the ciphertext sparse. So if you have a sparse ciphertext, you multiply by a sparse error vector, you can argue that the errors don't grow too much. But the problem is, as we compute, we get less sparse. So we really get this sort of diminishing returns in this computation. And so I think a really interesting question would be, can you in any way sparsify these ciphertexts? And this really is a target that could then let you maybe get more homomorphism and compute more interesting functions. The second approach, which Surya already alluded to, that I wanted to mention would be to sort of follow in the footsteps of Gentry and try and find a way to bootstrap. So really, what this would mean for us would be to find a linearly homomorphic encryption scheme where you can take its decryption function and homomorphically evaluate it under our somewhat homomorphic scheme. Because if you could do that, then you could introduce this cycle, and you could sort of loop and keep computing forever. But really, the barrier to this right now is that we don't have linearly homomorphic encryption with cheap enough decryption. So what you would need is decryption that you could write as a polynomial with degree sort of less than log lambda and poly-lambda monomials. So we don't know whether this can exist, and we have some thoughts as to why it seems hard. And finally, the last thing I wanted to mention is that building fully homomorphic encryption would be very interesting, even if you have to add in a little more. So I'll even give you leeway in terms of the assumption. Maybe you can use bilinear maps or a little more. So really anything that doesn't imply I/O and that's not LWE would be new and would be very cool. So yeah, thank you so much. This talk was about how we can use sparse LPN and linearly homomorphic encryption to build somewhat homomorphic encryption. I think there are tons of open questions, and yeah, you can find our paper online. Yeah.
So intuitively, if you compare kind of similar level of computation on like GSW scheme and you do for small numbers versus multiplication in your case, to me it seems like your scheme would be more efficient, but maybe it's deceptive. So did you try to do the comparison? Different assumptions.
Yeah, it's a good question. So here I think you can really take advantage of this sparsity to only sort of do the parts of the computation that are going to affect the final output. Right? So at the end, you only need the last row of your final ciphertext matrix. So in the step before that, you can only sort of materialize the rows of that ciphertext that affect this last row, and so on. So I think I'm, similar to you. When the degree is low, actually quite optimistic about, concrete efficiency. But that being said, we haven't estimated any parameters yet, so we don't know. But again, these parameters really only affect the size of the evaluation key. So in the online phase, they shouldn't really come in. Yeah?
During evaluation, since you moved to kind of like this bigger ciphertext, so it seems like the space complexity of an evaluated algorithm that grows with the maximum size of the function f itself.
Yeah. So it, let me move back. It does grow with the size of f. Yeah,
To avoid it? Because it just, ideally you would want, if I just want to do multiplication, I don't want just multiplication, or just, let's just say, ignore multiplication, let's just say addition. If I just want to add two ciphertexts, I don't want to say, okay, hey, to add two ciphertexts, although the entire computation is really big, I need to spend as much time as to sort of just here.
Yeah, okay.
Function.
So my answer is sort of a cop-out, because I think for addition you can avoid it by just immediately going to scheme 3. You immediately jump.
Then you lose
the ability to multiply later. Yeah. So we don't know currently how to make this more efficient. So that would be really cool also.
Yeah, is there hope to get some sort of perfect completeness like you can get with the LWE schemes?
Yeah, it's a good question. So what I would imagine doing now to reduce the correctness error is just run this, say, lambda times, and then take a majority vote of what that answer was, and you should get the right answer. I guess even with the LWE schemes, there's some error growth. So there's some small probability that the noise might overflow if you use, say, Gaussian errors. But yeah, we don't know beyond that. It's a good question also. Yeah.
Somebody asked you, but I might not understand the answer. So you're saying is a current thing, if let's say you want to do 7 multiplication, and some proved I know the first 4 multiplications and somebody else knows the other 3. You cannot do like first do 4 multiplications and only keep those purple ciphertexts and then do the remaining 3. You kind of need to commit to the whole 7 multiplications in advance. I mean, the whole kind of thing. You cannot do it like in 2. Like, I'm just saying, you can do like F1 composition F2, where F1 F2 is within your budget.
Yes, you can do that, but you have to stay sort of in sparse LPN land. You
Yeah.
can't jump to linearly homomorphic encryption because then we don't know how to come back. Yeah.
So you said you had some thoughts about getting these type of encryption scheme that has very
Yeah.
low depth or low multiplication.
Yeah.
And what were those thoughts?
Yeah. So unfortunately, it's the converse, where we have some thoughts that it should be hard. And the reason for this is because you can think of, if you had a way to bootstrap, it would sort of give you a gadget to go from one sparse LPN sample to many sparse LPN samples with not much higher sparsity. And really, like, you could just keep bootstrapping and you can get many, many ciphertexts, right? And so really, the attacks on sparse LPN or on LPN in general get much better the more samples you have. And so there's some worry that, if you had such a gadget, you could use this to make the scheme itself insecure, because you'd be able to get too many sparse LPN samples and then break it.
Or at least get better algorithms.
Yeah.
For sparse LPN that we didn't know before.
Yeah.
So it's not necessarily that negative, but it seems hard.
Yeah.
And related, like if I gave you like a tiny bit more magically homomorphism,
Yeah.
would it be like the degree or the number of monomials you'd want?
The degree.
Okay,
So
you
if
don't care about polynomials.
Yeah. So really, to be able to bootstrap, all you need is degree more than log lambda. So any super constant function in like more than log lambda, then you could bootstrap and you'd be golden. So really, that's where the ceiling is right now. Cool. Yeah. Thank you so much.